All right. Part 8.2, merge operation. In this video, we want to discuss the key operation, merge operation, in this new sorting algorithm, merge sort. Yeah. Here, the situation is pretty similar to that of the insertion sort. In the insertion sort, the main operation is the insertion operation. So you can see if we get that insertion operation, then the whole sorting algorithm is there. Here, we have the similar situation. If we can do just one merge operation for the general case, then we almost get there. All right, so let us start. Yeah. Now, let us look at the whole problem. So let us, from the overview part, look at the whole situation. Now, the first question, how to achieve balanced summaries. Now we need to do divide and conquer. When we do divide and conquer, we have one special goal in our mind. We want to achieve balanced summaries. All right. So here the idea is pretty straightforward. Yeah. Whenever we merge two summaries, we make them of equal size. So that is, we can call our strategy. Yeah. That is our current strategy. Yeah. All right. So here the question, let me use this line segment to represent the whole data array. Yeah. Now we need to do divide and conquer, right? So the first step, we want to split this array into two subarrays. Yeah. But when we do that, we have a chance to make that decision. So we use this strategy. Make the split as even as possible. Okay, here we can call it almost even, because based on the number of elements, even number of elements or odd number of elements, the worst we can do, if we try our best, the worst we can do, the difference of the size is 1, right? So when we have odd number of elements, the worst we can do, one subarray has one more element than the other. Yeah. All right, so based on that, we can do the splitting everywhere when we have a chance to make that decision. Yeah. All right, so let us work on this array. First, we just split right in the middle, if possible, or near the middle. Yeah. After that, the remaining two subarrays we have right now, we do the same thing. Split in the middle, or near the middle, and so on. We keep doing that, keep splitting all the way down to the bottom. Eventually, we have to stop, right? Yeah. So stop splitting when each subfile, small little subfile, contains one element. Now you only have one element subarray, you have to stop, right? So that is the end point. Yeah. After that, then the merge step. Can we do the merge step? Yeah. So the merge two adjacent subarrays, right? After that, we have individual sorted subarrays, a sequence of sorted subarrays. So then we merge two adjacent sorted subarrays again and again. So the subarray sizes become larger and larger. Yeah. And finally, we get one final sorted array. That is the main idea here. Main idea. So the result, we get a whole array sorted. How simple it is. Look at this whole procedure, how simple it is. You can see the splitting part quite trivial, right? Yeah, just split near the middle. Yeah. Quite trivial. Yeah. Nothing special we need to do. Yeah. After that, you can see the main step is the merge step. If we can solve that main step merge, we get whole problem sorted. Because during the split, we always follow the balancing principle. So you can see, as a result, we hope we can, by using this way, we can avoid worst case performance, worst case efficiency. All right. So next, we focus on the merge step. If we solve it, we're almost there. Yeah. All right. So let's go to the next step. Next step, I just use a diagram. A array, A subarray, B subarray, they have the same number of elements. Let us merge these two ordered subarrays. Now, when we start here, we just use the brute force method. Here, actually, we do not have anything special to use, just the brute force method. Right? So when we start, we look at the first element in each subarray and we compare them. When we do the comparison, we have a minimum number and a maximum number. Although only two numbers, two elements, but one smaller, one larger. So we use the notation at min 0, another max 0. Yeah. After that comparison, look at how much we can do with that first comparison. What we can do, we know we can do something useful for our destination array. So this is our destination array, merging two ordered arrays. So we create a new empty destination array, and then we will put elements one by one in this destination array. The first one we can place there, the min 0. After one comparison, we know the min 0 must be the first one, because this minimum number is the minimum of both subarrays. That's obvious, right? We compare the minimum of each subarray. The smaller one is the minimum of the whole array. After we get a minimum of the whole array, that one, we can put it as the first element in the destination array, and we call that action, we put it in place, right? So if we do the summary a little bit, after one comparison, we place one element in place. Now, let us keep doing this again and again. All right. Yeah, here we just assume, suppose B0 is the larger one. So that's the case one. Although we have another case, right? A0 is the larger one. That's another case. But we know if we discuss just the one of the cases, it should be good enough. Yeah. All right, so after that, max 0, we can use it to compare with A1. The first element in the other array that has not been processed. Yeah, A1, that is A1. A0 is already placed in place. Yeah, so A1, the next one. Yeah. Assume min 1 is the smaller one between A1 and B0. After the second comparison, we can place min 1 in place, right? Yeah. So here you can see we keep doing comparison like that. After every comparison, we can place one element in place. Until we reach the last one. Now, here we want to look at the worst case. Yeah. With this idea, we can place all the elements in place, but now we look at the worst case. The maximum number of comparisons we need to get the whole array ordered. Yeah. Yeah, for the worst case, actually, we just get one observation. So that is, we need to do comparison as many as possible, right? Yeah. So we keep placing one element in place at a time and doing this again and again and until we reach the last element. But the last element, we don't need a comparison, right? Only one element left. So we don't need to do any comparison when we reach the very last element. So that means before the last element. Here. For every new min added into the destination array, we may need one comparison, except the last one. Yeah. The very last one, no comparison needed, right? So if we can get that happen, then that is our worst case. Worst case. Yeah. So we can get the number of comparisons for the worst case. You can see the total number of elements minus 1. Yeah. Because before the last one, each element corresponds to one comparison, right? So the total number of comparisons equals the total number of elements from both arrays minus 1. So you can see the answer is 2k minus 1. Yeah. Then if we go back to the here we want, after we get the answer, we want to look at the general merge step. So we can extend our result to the general case. So what is the general case? A subarray, B subarray, they may not have the same size. The first one has m elements, second one has n elements. Yeah, the size is different, m elements and n elements. In this situation, what should be the answer for the worst case? That's pretty straightforward. Yeah, still the same procedure. Every comparison results in one element in place, except the last element, right? So if you have that case happen, then the number of comparison still the same, total number of elements minus 1. The total number of elements m plus n, then minus 1. So that's the answer we have for the general case. Yeah, general merge step. Sometimes we may need to do the general merge step, right? Yeah. All right. Then for the best case, here we almost get the best case, but this time we change our standard or requirement different. Yeah. This time we want to look at it. What is the minimum number of comparisons we need to get whole sorted array? Yeah. So we just need to get one special property. Okay, one special property or strategy. Yeah. The strategy is try to exhaust one of the two arrays as early as possible, right? Yeah. What do you mean exhaust? Because when you put one element in place, every time one element in place, then under a special situation, you may exhaust one of the two subarrays, right? Yeah. Here, we want to exhaust one of the subarray, then the remaining of the other subarray, we do not need to do comparison. We just put all the elements in place, right? That is the property we observed. Yeah. All right, so with that observation, we can get our conclusion. Yeah. When we exhaust one of the subarrays, which one corresponds to the smaller number of comparison? Yeah. This case exhausts the shorter array. Yeah. When you have two subarrays, we assume one is shorter, the other is longer for the general case, right? Yeah. Still, here we consider the general case. When we have shorter array, longer array, then for the best case, we just exhaust the shorter array as early as we can, right? So the answer is the best case efficiency, the size of the shorter array. So what's that number? Yeah. The minimum of m and n. That is the answer, the best case. The minimum of m and n. Yeah. All right, so we complete part 8.2. Yeah. You can see we're almost there for the merge sort. All right, so let's stop right here.